In this video, we're going to take a look at a Leetcode problem called longest increasing subsequence. So we basically given an integer array and we want to find the longest increasing subsequence. And increasing subsequence means that for each and every single of those elements, the elements that's right next to each and every single element must be bigger than the current element, right? And in this case, you can see that we are, the subsequence basically means that we have a array, and in this case a subarray, and this subarray the elements inside the subarray doesn't have to be right next to each other, right? You can see that we have 3, 6, 2, 7, which is 3 is right here, 6 is right here, 2 and 7 is right there, right? So it doesn't have to be right next to each other, but you can see that the order follows the same, right? Without changing the order of the remaining elements. So you can see here we have an example of this, right? And the longest increasing subsequence in this case is 2, 3, 7, 101, right? And with a size of 4. And you can see here we also can have an option of, in this case, 10 and 101, but the size of that sequence is going to be just 2. And we can also have 2, 5, 7, and 18, or 101. But we don't really care about what's inside the sequence. We just want to know what's the longest increasing subsequence size, right? So we're just returning the 4, right, in this case. And you can see we also have another example where we have 0, 1, 0, 3, 2, 4, 3, 2, 3. And same thing here, I can have 0, 1, 3, 0, 1, 2, and 3, right? In this case, because I cannot have 0, 1, 3 because that will give us a size of 3. So I can only have 0, 1, 2, and 3, right? So this will give us a size of 4. And you notice here that this is not increasing. Like you can see that all the values are equal to each other. So in this case, we're just going to have 1 because initially, if we only have one element in the array, and this is our subsequence, then we have one increasing element. But if we have those elements that are all equal to each other, then in this case, we're not increasing at all. We're not decreasing. We're not increasing. Therefore, there's no, in this case, here to here, is not increasing at all, right? So this is not the longest increasing subsequence. Or I should say, this does not count as an increasing subsequence. So we're just returning 1 because if we only have one element, right, the first element is the increasing subsequence, right? And then you can see here the constraints that the length of the array must be bigger than or equal to 1. Right? So we will not have an array that is empty. So how can we solve this problem? So let's say we have an example of 1, 2, 4, and 3. So in this case, the longest increasing subsequence obviously is going to be 1, 2, 3 or 1, 2, 4, right? So in this case, the size of 3, right? So in this case, what we can do is that for the brute force approach is that we can try for each and every single combination and see if that's the longest increasing subsequence that we found so far, right? So in this case, what we're going to do is we can actually start at any position to find the longest increasing subsequence. So if I started here, right, the longest increasing subsequence that I can see or that I can find is 1, 2, 3. If we were to start here, the longest increasing subsequence that we find if we start at 2, or in this case index 1, is just going to be 2, right? In this case, I can have 2, 4 or 2, 3. And if I start at index 2, longest increasing subsequence that I can find is 1. So you can see that this element I can find 3, the longest increasing subsequence for this element is just going to be 3, right? That I can find if I start here. The longest increasing subsequence that I start here is going to be 2. The longest increasing subsequence if I start here is just 1. And the longest increasing subsequence if I start here is just 1 as well, because I don't have any elements that are bigger than the current element that we can add onto our subsequence, right? So in this case, out of all those elements, the biggest is gonna be 3, right? So the max, we're gonna have a variable to keep track of the maximum longest increasing subsequence that we have seen so far, and we're gonna return that at the end, right? So now how can we do this in a recursion, right? In this case, a top-down approach. So in this case, initially, if I have the same example, like 1, 2, 4, and 3, I have nothing in our array, right? So, and then what we can do is I can add 1, right? I can start at 1 for our current subsequence. I can also start at 2, and I can also start at 4, I can also start at 3, right? And here, if I were to start at 1, in this case, I can add 2 because 2 is bigger than 1. I can also add 4 In this case, 4 is also bigger than 1. I can also add 3, and 3 is also bigger than 1, right? And if I add 2, I can also add 4, right? In this case, I can add 4 onto our subsequence, and I can also add 3 onto our subsequence as well, because these elements are all bigger than 2. But here, I cannot add 3 because 3 is not bigger than 4, right? And same thing here, I cannot add 3 because 3 is not bigger than 4, so we cannot do that. So in this case, this is the longest increasing subsequence that we can find, is that we know that this is the last element that we can add onto our subsequence. So we're just going to return the current element's value. In this case, the current element, right? In this case, we found 1, so we're going to tell parents, say, hey, for this element, if we add just 4, right? If we only add 4 onto our subsequence, then there's only one, in this case, only one longest increasing subsequence, right? If I only have 4, I cannot add any more elements because I cannot add 3. So in this case, for this position, I can only have 1 longest increasing subsequence. And if I only have 3 in our subsequence, the longest increasing subsequence that I can add, or in this case, it's just 1, right? In this case, I cannot add any elements more because there's nothing after 3. So in this case, we cannot add any more, so we're going to tell its parent, say, the longest increasing subsequence, right? The longest increasing subsequence for index 0, 1, 2, 3, right? 0, 1, 2, 3 is just going to be 1, right? The longest increasing subsequence at 2, right, is just going to be 1 as well, because there's no elements that are bigger than 4 that we can add onto our subsequence. So we're going to return back to its parents. So the parents stack will say, okay, well, the decision that we chose, right, the longest increasing subsequence for the path that we traverse are all just 1, right? The maximum value is just 1. So for this current element, in this case, the longest increasing subsequence at index 1, right, is going to be the maximum value of all those values right here. In this case, all those values, right? If I want to add 4, if I want to add a 3 onto our subsequence, the longest increasing subsequence for them is just going to be 1, the maximum, plus the current element, because we're going to add 2 onto our subsequence. So we're going to have a 2, right? In this case, I can have 2 and 4. I can have 2 and 3. So these are all like increasing subsequence, right? So in this case, the longest is going to be 2, right? And now we're going to return back to its parent and say, I have 2. In this case, the longest increasing subsequence for this element is going to be 2. And the parent stack, right? The parent element in this case is just 1, right? 1 in this case has also 4, has also 3. In this case, I can add like 1, 2, right? I can also add 1, 3. I can also add 1 and 4, right? So these are all like valid combinations. So in this case, if I add 1, 2, right, it will give, in this case, this, if I add 2, this has a longest increasing subsequence of 2, plus this current element, and it will give us a longest increasing subsequence of 3, right? And if I add a 1, 3, then in this case, there's no elements left. So the longest increasing subsequence for element 3, or index 3, is just 1. So 1 plus 1 is just 2. And longest increasing subsequence for index 2 is just going to be 1. So 1 plus 1 is just going to be 2. So in this case, you can see that the maximum value out of all those 3 positions, if I add 1, if I added 4, if I added 3 for the second element in the subsequence, in this case, 2 has the largest value, so we're just going to add 2 onto our subsequence, right? So in this case, the longest increasing subsequence for this element right here is just going to be 3, right? So 2 plus 1 is just going to be 3. And then we're going to return back to its parent and say the longest increasing subsequence if we are starting at 1 is just going to be 3. And same thing if I want to know if the longest increasing subsequence if we are starting at 2. In this case, we already compute this value, right? In this case, index 1, we already compute this value. The longest increasing subsequence, if we are starting at 2, is going to be 2. So we're just going to return its parent and say, okay, the longest increasing subsequence is 2. If you're starting at 4, is 1, right? Because we already compute this value. And same thing here, index 3. Longest increasing subsequence at index 3 is just going to be 1. So we're just going to return that to the parent, say the longest increasing subsequence for this element is just going to be 1. So you can see that we have 3, we have 2, we have 1, we have 1. So what's the largest? In this case, is 3, right? So what we can do is that we can use this type of approach top-down memoization approach. So this will give us a time complexity of n squared and a space complexity of linear, or big O of n. So to do this in code, first I'm going to create a global variable called integer nonce. So we're going to set this to a global variable, and then we're also going to create a cache array. So in this case, this cache array basically stores for each and every single element that we have in nums. We want to know the longest increasing subsequence for each and every single position in nums, right? So we're going to have a cache array. So this dot cache is equal to new integer with the size of integer n is equal to nums.length, so it's the size of n, right? So what we're going to do now is we're going to create a helper function, and this helper function is going to return the longest increasing subsequence with the given index, right? So what we're going to do is because we're going to start at any of those elements, so we're going to iterate for each and every single element that we have, right? For each and every single elements. If we were starting here, what's the longest increasing subsequence, right? So in this case, cache at I is equal to helper. If we're starting at this position, what's the longest increasing subsequence? And we will save that in our cache. And at the end, we want to return the maximum longest increasing subsequence that we have seen so far. So the max initially is equal to 0. And then what we're going to do is so in this case, max is equal to the maximum value, either the maximum longest increasing subsequence that we have seen so far, so max longest increasing subsequence, or is going to be the longest increasing subsequence for the current position, right? So let's try to implement the helper function. So now to implement the helper function, we're going to create a helper function that returns an integer value, which is the longest increasing subsequence for the current index. So index. Okay, so what we're going to do is we're going to see, first we're going to check to see if the current element is already being pre-computed, right? In this case, if the current value is already being pre-computed, then we can just return that value. So cache at index. If cache at index does not equal null, then we can just return cache at index, right? We just return the pre-computed value. And then what we're going to do is we're going to iterate the remaining elements, right? In this case, because we know the current index, so in this case, integer I is equal to index, while I is less than nums.length, I++. So we're going to iterate the remaining elements. And for each and every single elements that we have, if the current element, if nums at I, right, is actually bigger than the current value, so let's probably create a variable called current value, so integer current val, right? So the current value is nums at index. So if current val is less than the remaining elements, the current remaining elements, then what we're going to do is we're going to do a DFS to search its longest increasing subsequence, right? So in this case, to get the current longest increasing subsequence, I need to know the children, right? In this case, the longest increasing subsequence for the remaining elements, so that we can be able to make that decision. So in this case, the max longest increasing subsequence initially is 0. So for this element, in this case, the maximum longest increasing subsequence is either math.max, the longest increasing subsequence that we have seen so far, or is going to be helper at I, right? So in this case, I is going to be the current remaining element. So we're just going to keep iterating until we find the maximum longest increasing subsequence for the remaining elements. And then for the current elements is going to be cache at index, right, is equal to the maximum longest increasing subsequence plus the current element, because we have to add the current element onto our subsequence, right? And at the end, we're just going to return cache at index, right? And this is basically how we solve the problem. So now let's try to run our code. And let's try with a few more examples, right? And now let's try to submit. And you can see we have our success. So this is basically how we solve this problem in a n squared time complexity, right? Because here you can see for each and every single element that we want to find the longest increasing subsequence. And for each of those elements, for the answer, right, the longest increasing subsequence is going to be the maximum longest increasing subsequence for each and every single element. If we were to start at 1, if we were to start at 2, if we were to start at 3, right, out of all those subsequence, the increasing subsequence, we want to find the max, right? And that's what you see here. Like if we pre-compute this value, we're going to return that pre-computed value. And if we haven't computed that value before, we're just going to calculate it. And for each and every single element, for each and every remaining elements, right, if the current element is actually less than the remaining elements, the current remaining element, then we're going to do a DFS to search its longest increasing subsequence, right? And then out of those, we're going to find the maximum for the maximum longest increasing subsequence for the remaining elements. And then to compute the current longest increasing subsequence, it's going to be the maximum longest increasing subsequence for the remaining elements, plus the current element will be the longest increasing subsequence for the current position. And we're going to return that back to the parent. So to solve this problem using a bottom to up approach, let's say we have the same example of 1, 2, 4, and 3. So the longest increasing subsequence, if we were to start at the bottom, right, the last position, in this case, is just be 1 because I can only add 3 onto our subsequence. If I start at 3, then there's nothing that we can add. And if I start at 4, there's also nothing that I can add after because all the remaining elements, in this case 3, is less than 4. And if I have a 2, I can add, if I start at 2, right, add 2 onto the subsequence, I can also add 4, or I can have 2, 3, or I can have 2, 4, right? So in this case, the maximum or the longest increasing subsequence for this position is 2. And the longest increasing subsequence for this position is I can add 1, 2, 4, I can add 1, 2, 3, right? So the longest is going to be 3. So what you notice here is that if I start at the bottom, then it's automatically 1 because in this case I have only one element that I can add, and there's nothing on the right where the remaining elements that we can add for this element, right? So in this case, the longest increasing subsequence for the last position is always 1, and the longest increasing subsequence for the current element, right? In this case, if I want to find the longest increasing subsequence for the current element, then it's going to be the longest increasing subsequence for the remaining element, right? The maximum longest increasing subsequence for the remaining elements, and the remaining elements must be bigger than the current element to take it as account, right? So in this case, if I want to iterate the remaining element, and if the current element is actually, if the remaining current element is actually less than the current element, then we cannot take that as account because we cannot add 3 onto after 4, right? So we want to find an element that's bigger than the current element. In this case 4, we do not have any elements bigger than 4, so I cannot find any element. So the longest increasing subsequence is just this element itself is just 1, right? And same thing for 2. If I want to find the longest increasing subsequence for the remaining elements, in this case I have 4, I have 3, and both of them has a longest increasing subsequence of 1. So in this case, 1 plus the current element, because the current element is, there's only one element for the current element, so 1 plus 1 is just 2. And for 1, in this case, I can go and iterate or do a linear search for the remaining elements to find the longest increasing subsequence that's the element must be bigger than the current element. And in this case, we have 2. 2 has the maximum longest increasing subsequence. So 2 plus the current element is just, in this case, current element only have 1, right? We only have one element for the current element, so just 1 plus 2 is just 3, right? So this will basically bring the time complexity, where actually the time complexity is still the same because it's going to be n squared, right? For each and every single element, we had to iterate n number of times, right? And then for the space complexity is also going to be n, right? If big O of n, we're using a linear or integer cache array to store the pre-computed value, right? And we're going from the last position of the cache array all the way to the first element in the cache array. And throughout, we want to find the maximum longest increasing subsequence for the entire array. So now let's try to do this in code. So to do this in code, first what we're going to do is we're going to create the integer cache array. And let's create a variable called n. So n is equal to nums.length. So in this case, cache has a size of n. So what we're going to do is that we're going to iterate. But we know that the first element that we have in our cache, or sorry, the last element that we have in our cache, n minus 1, is always going to be 1. Because if I have only one in this case, because there's no elements that we can add, or there's no remaining elements that we can add onto this subsequence if we're starting at the last element, right? So in this case, the longest increasing subsequence for the last element is going to be 1. And then we're going to start at I is equal to n minus 2, the second last element, all the way to 0, right? For each iteration, what we're going to do is that we're going to find the maximum, the maximum longest increasing subsequence for the remaining elements. Longest increasing subsequence for remaining element. Okay, initially it's going to be 0. So longest increasing subsequence for the remaining elements. So we're going to iterate for each and every single iteration, right? We're going to have a j is now equal to I plus 1. So while j is less than n, so j plus plus, we're going to iterate the remaining element, and the current element in this case, the current val is equal to nums at I. So in this case, if current val is less than nums at j, if we know the current value is less than nums at j, then we're just going to say the maximum longest increasing subsequence for the remaining elements is equal to the maximum, either the current value that we've seen so far, the current longest increasing subsequence that we've seen so far, or cache at j, right, which is going to be the pre-computed value for the current remaining element. And then at the end, after the iteration, we're going to get the longest increasing subsequence. So current cache at I, right, is equal to is equal to the maximum longest increasing subsequence for the remaining elements, plus 1, because in this case the current element is we have to add the current element onto our subsequence, right? So that's basically the longest increasing subsequence for the current element. And then what we're going to do at the end is we have to find the longest or the maximum longest increasing subsequence if we are starting at the first element or the second element or the third element, or basically the longest increasing subsequence throughout the entire cache array, right? So what we can do is we can do a linear search at the end. After this loop, we can do a linear search to find the maximum value, or we can have a max longest increasing subsequence, which is equal to 0 initially. And for each and every single iteration, we're going to find the max longest increasing subsequence is either the current max longest increasing subsequence or cache at I. Right? And then at the end, we're just going to return the maximum longest increasing subsequence that we have seen so far throughout the entire cache array, right? So this will give us a time complexity again, n squared, and space complexity of linear. And now if we were to submit, you can see we have our success. Nope, that's not going to happen because I can have 1 here, right? In this case, I can have 1. Because if we have 0, if we only have 0, then the longest increasing subsequence is just 1, right? Or if I only have 1 element, then the longest increasing subsequence is just 1. And now if we were to run the code, you can see we have our success, right? So basically, this is how we solve this problem in a bottom-to-up approach. So how can we optimize our current existing solution? Well, what we can do is we can use binary search plus dynamic programming, which is something that we just did. What we're going to do is that here you can see we have a given array, and we can either have 2 subsequence. First of all, ignore the 6, right? Just first of all, ignore the 6. We can either have 1 to 8, in this case 1 to 8, or 3, 4, 5. 3, 4, 5, which is right here, right? So which one's better? What do I mean by that? Well, which one is actually shorter? In this case, 5 is less than 8. Therefore, 3, 4, 5 has more room to expand. In this case, if we have another element, in this case 6, we can easily add it onto this array list, right? 3, 4, 5, we can add a 6 here, but if we add a 6 onto 1, 2, 8, it's not going to be an increasing subsequence, right? We want a increasing subsequence. So what we're going to do instead is we're going to use a cache array. Basically, for each element in the array that is given, we're going to either extend the longest subsequence, which is the cache array we have, or replace an element to make a sequence better, right? So here, I'll give you an example here. So here you can see we have a given array. So we have 3, 4, 5, 3, 4, 1, 2, 8, 5, 6, right? We're iterating each and every single element in the num array. Then what we're going to do is we're going to have a cache array to cache the longest subsequence, right? In this case, so here initially we have one element, so we just add it to the cache array, and we're basically trying to build a longest subsequence in this cache array, right? And then we added 4. 4 is bigger than the current element, then we just append it onto this array, right? Then we can have 1 here. So 1, because 1 is, in this case, is not bigger than the last element, then what we're going to do is we're going to use a binary search, right? We're going to talk about binary search in a second, but basically what we're going to do is we're going to replace this 3 here with 1. And then basically here you can see we have 2. So 2, in this case, we basically is not bigger than the last element, but what we can do is we can use binary search to find its position in the cache array. In this case, it's going to be this position. So we're going to replace 4 with 2, right? And it makes sense because up to this current point, the longest subsequence is either 3, 4 or 1, 2, right? So it doesn't really matter which order we go to. What it really matters is, do we have a longest subsequence, and what's the size? In this case is 2, right? Either we have 1, 2 or 3, 4. So the longest subsequence at this current position is 2. So that's why we have 1, 2. And we have 8. Now we append 8 here, right? Append 8 at the end. In this case, we have 1, 2, 8. And then because 8 is bigger than 2, that's why we append it here. And 5 is not bigger than 8. So what we can do is we can just replace 8 with 5, right? And it makes sense here because 5 up to this current point, the longest subsequence, the longest increasing subsequence is basically 3 elements. It's either we can have 3, 4, 8, or 3, 4, 5, or 1, 2, 8, or 1, 2, 5. Right? And if we were to add 6, the best solution we can have is append it onto our current existing list. In this case, our current existing list is 1, 2, 5. If we have something like 1, 2, 8, we cannot append 6. So that's why we have to use this kind of style to append elements, right? In this case, we have to use binary search. And let's talk about binary search. So in Java, we have this arrays.binary search method. Basically, it takes this array that we want to search in, and the target, the element that we want to search inside this array. So in this case, we want to search 8 in this case. What it will return? It will return -6. Well, basically, it will return the range, the position where 8 should supposed to be in. In this case, 8 is supposed to be at index 0, 1, 2, 3, 4, 5. In this case, we have index 6, right? So what we're going to do is we're going to minus this position. So in this case, if we were to, actually we have to add 1. This will turn into a -5. And -5, we're gonna times -1. It will turn into a positive integer 5. And 5, you can see 5 is actually equal to the size of the array, right? Or I should say is bigger than the last element's index in the array. Then what we're going to do is we can just append 8 onto the array. And for 4 is the same thing. If we want to find 4, in this case, it's going to be 0, 1, 2, 3, 4. In this case, the last element. We plus 1 is going to be 3, and then we -3, and then we're going to times -1. In this case, it's going to be a 3. Now what we can do is we can just say 0, 0, 1, 2, 3, and 3 is right here. We can just replace 4 with, we can just replace 5 with 4. This way we can be able to, like I mentioned, replace element to make the sequence better, right? To make the subsequence better so that we can insert more elements. In this case, here you can see we have 0, and 0 in this case is -1. -1 plus 1 is 0, and then in this case, the absolute value of 0 is 0. So what we're going to do is we're just going to replace 1 with 0, right? So let's try to do, so I think you get a good understanding of how we're going to do this. Now let's try to do this in code. So to do this in code, we can either use a static array or a dynamic array. I'm just going to use a dynamic array in this case. So we're going to use a list of integer because we are unsure of the size of the array. We can use a variable to keep track of the current size. And we know that the size of the array is equal to this, it must be less than the size of nums. So we can either have a static array with a variable of length to keep track of the current size, or we can use a dynamic array. So for demonstration purposes, I'm going to use a array list. Let's just call it cache is equal to new array list. Okay. And what we're going to do here is pretty simple. We're just going to iterate each and every single element. So num. Right, and what we're going to do is we're going to, for that element, we're going to search that in the cache, in the cache array to see if we actually find the element. In this case, is equal to arrays.binary search bit. It only takes a array, right? In this case, what we can do is we can just convert the array list into array. So in this case, cache arrays, I should say cache dot to array. This method will take this array list, convert it into array. And what we're going to do is we're going to pass in the element that we want to search, which in this case is num. So just like I mentioned before, it will basically return a negative number, but it also gets to return a positive number if we found that element. So we're going to check to see if index is actually less than 0. If it is, what we're going to do is we're going to convert it into a positive number. And we also have to make sure that we plus 1 to it. So index is equal to negative index plus 1. Okay, this will convert into a positive number, but we also have the plus 1 to it. And then what we're going to do is for the element we want to see if it's outside of the size of the array list. So if cache.size is less than or equal to, right, is less than or equal to the index, then we know we have to add it onto the cache array list, right? So in this case, we can just add the num append it onto the list. If it's somewhere inside the list, right? If it's somewhere inside the list, then all we have to do is we have to set cache.set. We set index to this element, to the current num. Okay, and then our job is done. All we have to do is we just returning, because we don't want to. We're not returning what's inside the list. All we are returning is the size of the list. So in this case, we're just returning, this case, cache.size. Okay, let's try to run the code. And here you can see we have accepted. Now let's try to submit. And now you can see we have our success. So basically, this is how we bring the time complexity down to n log n